Welcome and thank you guys for tuning in to another Algebra 2 lesson via online instruction. Today we are going to be taking a step further from the notes that we just finished up on linear systems with two variables. We are going to be expanding to a linear system now with three variables. So it's going to incorporate a lot of the ideas that we just worked on, but it's going to take them a step further. Now, just kind of as a refresher, what we were focused on in the previous lesson was essentially if we had a coordinate plane, um, an XY coordinate plane. We're familiar with this. You've worked with this a lot and throughout your academic career. We could have two different equations that represent two lines. So as long as these two lines are not parallel, they will intersect. As long as they're not parallel with different y-intercepts. So the intersection point there would then be the solution of these two equations, finding or essentially solving for both the variables x and y. Now, what we can have is we can go a little bit further. We can still have the x and y coordinate planes or axes, but also include a z-axis, a third axis here. So this would be the x-axis, the y-axis, and then the z-axis. So if you think about a 3D object, so let me just roughly sketch a 3D object here. This is essentially what this plane is representing. So we have an axis that is the height, an axis that is the width, and then an axis that is the depth of this object. Now, we're not going to do a lot of graphing on a three-dimensional plane. That's for a class down the road. But let's say we had a point, let's say we had 1, 0, 3. If we think back to previous, if I had 2, 3, from the normal xy plane, my x is 2, my y is 3. Now, if I have 1, 0, 3, my x is 1, my y is 0, and then my z is 3. So basically what I would be doing here is going to the right one. I would be going up or down 0, and then be moving across the z-axis 3 units. And so this point would end up somewhere, 1, 2, 3, this point would end up somewhere in there, okay, on a three-dimensional aspect. So these points can be graphed and they can be plotted. Again, we're not going to focus too much on the plotting of points in 3 dimensions. What we're going to work on is finding these solutions. And so we don't have graphing calculators, or most of us don't have graphing calculators that have a third dimension on it. So all of our techniques here are going to be to find algebraic solutions. The first thing that we want to be able to have, a skill that we want to be able to use, is to determine if a solution that we find is actually a solution, or basically to check our answers. So in problem number 1, it says, determine if the ordered triple 1, -2, 3 is a solution to the systems shown below. So again, like I said on the previous page, the numbers represent values for variables. If it's three-dimensional, the first number is an x, the second number is a y, and the third number is a z. And so we can find out, or we can check to see if this is going to be a solution by simply substituting in the numbers. So if I take each equation here, I'm going to put in, let's start with the first equation. I'm going to put in a 1 for the first equation for x, then a -2 for y, and then a 3 for z. So we can replace x, y, and z with the numbers that are given to us in that coordinate triple. And then we can evaluate. So 1 plus 4 times -2 minus 3 equals -10. So this triplet of numbers is a pair, or sorry, is a solution for the first equation. It's good. We can't just check one equation though. We need to make sure that this is going to be a solution for all three equations. So let me check the second one. 2 times 1 plus 5 times -2 plus 8 times 3. Again, replacing each one of the variables with the value that you get from the ordered triple. So 2 times 1 plus 5 times -2 plus 8 times 3 equals 16. Well, if I compare this second equation to the equation that was given to us in the system, the two answers are different. So when we input those values, it came out to give us 16. But when we input the values here, it wanted them to be a 4. So this set of numbers does not work for the second equation. So we would say that this is not a solution. Now, we don't know what the solution is for sure, but we know that it's not 1, -2, 3. So in order to find a solution, you need to substitute in those values and then see if those equations are going to be equal to what was given in the system. See if you can go ahead and figure out B. So pause the video and find out if the same triple 1, -2, 3 is a solution to that given ordered pair. Okay, so hopefully you have something that looks like what I show here on the screen. So again, I substituted in 1 for x, -2 for y, and then 3 for z. And I did that for each one of the three equations. And then I went ahead and typed all three of those into the calculator and found what they equal. And I listed that here to the right. So if we compare the substitution and evaluation of the equations, it's going to be equal in the first, the second, and the third cases. So for the second system, 1, -2, 3 is a solution. So in order to be a solution, the 3 points have to be able to substitute in for the three variables and to give you equivalent expressions as what was shown in the system. Now, again, the order is alphabetical. So the first number is x, the second number y, and the third number is z. Now, this is how we can check to see if our answers are correct, essentially. Let's take a look at how we can find answers. So basically, we're going to focus on one method. Like I said previously, most of your graphing calculators do not have the ability to graph in the third dimension, which is okay. So we're going to solve these algebraically. We're going to solve them using elimination. Elimination is basically the only method that we're going to have here that's going to be able to work. Now, let's take a look at problem number 2. What we see here is we have three different equations with three different variables. In the previous topic, we found out how to solve equations with two variables. So maybe if we had x plus y equals 2 and maybe 3x minus 2y equals -4. We figured out how to solve that expression. So what we want to do is we want to get this system that has three variables down into a system that has two variables. And we're going to do that by eliminating variables. So let me take a look at the third equation here. Notice that the third equation has only two variables. It has a y and a z. So this is an expression that is more similar to what we saw previously with the previous topic. If we can get another equation to have just a y and a z, then we can combine this with this third row here to be able to solve. So what I'm going to do is I'm going to number these rows. 1, 2, and 3. Now remember, with elimination, you want to get coefficients of a variable to be opposites. Now if I take a look at equations 1 and 2, somehow I want to combine these two equations to get rid of an x. So what I may see here is that equation 1 has a 2 in front of the x. So what I want equation 2 to have is a -2 in front of the x. I want to get rid of the x again because the third equation has just a y and z variable. So I want another equation with just a y and z variable. So what I tend to do is I tend to write this out as, okay, I'm going to use equation number 1, and I'm going to take -2 times equation number 2. So equation number 1 is 2x plus y minus 2z equals -7. I usually write it like this because that's going to help us keep track of work later on. Now I'm taking -2 times equation number 2. So -2 times x is -2x. Negative 2 times y is negative 2y. Negative 2 times z is negative 2z. And negative 2 times negative 1 is positive 2. Now, what I can do with these equations is I can add them. So I kept the first equation the same. I changed the second equation by multiplying everything by negative 2. Now I can add the two equations. So 2x plus negative 2x, those essentially cancel out. Y minus 2y would be negative y. And then minus 2z and minus 2z would give me a negative 4z. And negative 7 plus 2 gives me 5. So now I have this equation that's negative y minus 4z minus 5. So what's good about this is I can take equation number 3 here that only has two variables, and this equation that we just created by combining 1 and 2 that only has two variables to start a new system. So basically this is going to be equation 3 plus this other equation that we created. So negative 2y minus z equals negative 3, and negative y minus 4z equals 5. So now I no longer have to focus on that the three linear system equation. Now I can focus on a two linear system equation. And then we can solve this using any method that we've done in the past. So I'm going to use elimination again here. I'm going to take this second equation and multiply it by a negative 2. So what that gives me is negative 2y minus z equals negative 3. So I haven't changed that top equation. Again, now I'm just focused on this linear system right here. And that gives me a positive 2y plus 8z equals negative 10. So I'm just using a multiplication of negative 2 times everything here to rewrite the equation. Now what I can do with these two is add them. So negative 2y plus y cancels out. Negative z plus 8z gives me 7z. And negative 3, oh, sorry, somewhere I made a mistake. There we go. This should have been a negative 5 prior to this. So that 10 should be positive. Hopefully you caught that, but negative 7 plus 2 is negative 5. So this should be negative 5. Negative 5 times negative 2 is positive 10. There we go. Now 10 minus 3, or negative 3 plus 10 would give us 7. And now I can solve for z. Divide by 7. So z equals 1. So what I did here, again, was I used elimination to get rid of this x variable between equations 1 and 2. I did that because I wanted to get a two variable linear system. I already had one with just a y and a z as variables, so I wanted to create another with just a y and z as variables. Then I could take those two equations, so these two right here, and put those into a new system that we know how to solve. Now, once I know z, I can go back to any of these equations that I've been using and substitute to figure out other values. So I know z equals 1. So I'm going to go back to this equation right here, and I'm going to put in 1 for z. So this would be now negative y minus 4 times 1, which is 4, equal to negative 5. Add 4 to both sides, so negative y equals negative 1. Then to get rid of to get rid of the negative, I would divide by negative 1. Y equals positive 1. And there I have my solution for y. Finally, I need to solve x, so I need an equation here that has an x in it. So I'm going to go back to, I'm going to use this second equation before we changed anything. X plus y plus z equals negative 1. So x plus y, which is now 1, we did that down here, plus z, which is now 1, equals negative 1. So x plus 2 equals negative 1. Subtract 2 from both sides, so x equals negative 3. So that is my three solutions. X equals negative 3, y equals 1, and z equals 1. So in this, again, we want to use elimination to turn the system of three linear equations with three variables into a system of two linear equations with two variables that we know how to solve. Then we can solve for one of the variables and go back in and substitute until we can solve for the others. So my equations, my answers could be written as separate answers for the variable, but you could also put these together and write them as a single point, -3, 1, 1, and that would be my solution as x, y, and z is an ordered triple. So this is the method that we are going to use over and over again to solve linear systems with three variables. Let's take a look at another example. Example B. Now what we may notice in example B is that these equations, they do have an x, y, and z variables, but they're not written in the same format. So we did this in the last target. The first thing that we want to do when doing elimination is make sure everything is ordered in the same manner. So I'm going to go ahead and rewrite this system as 2x minus 5y minus z equal to -8 for the first equation. Then -x plus 2y plus 3z equal to 13 for the second equation. So making x come first, then y, then z. Then finally x, ooh, there's a typo on these notes. This should be a 3y here. By the time you guys get the packet, that will be fixed, but I just want to make sure it's fixed on the screen. So this would be x plus 3y minus z equals 5. So there's our system written in the correct order, making sure everything is ordered the same. Okay, so now what we need to do is we need to find a way to get from one system with three variables into one system with two variables. Notice that each equation here has three variables. So what we're going to have to do is use our elimination method twice. Now, if I take a look at equations, I'm going to list them. I'll make it A, B, and C this time. I'll just call them equations A, B, and C. What I'm going to look at here is I notice that B and C have already, the x values have opposite coefficients. So all that I'm going to do is I'm going to take B, I'm going to add C for my first step. So I'm going to take -x plus 2y plus 3z equals 13. And I'm going to add x plus 3y minus z equals 5. So if I take these two equations and I add them together, -x plus x is 0. 2y plus 3y is 5y. 3z minus z is 2z. And 13 plus 5 is 18. So right away, I can use the first two equations and combine the two of them to then give me, or to add together these opposite coefficients and get rid of the x value. So now I have an equation where I have just a y and a z. That's one equation though. I need two to create a system. So I'm going to go back and combine two different equations now, not b and c, but two different equations to get rid of an x variable again to give me just a y and a z, a different y and a different z. So let's take a look at a and b. Their coefficients for x are opposites, but they're not different number, the same numbers. So one's a positive, one's a negative, but I need to do something to b. If I said I want to multiply b by 2, then you'd be correct. So what I'm going to do here is I'm going to take a plus 2b. So I'm going to multiply b by 2 as I go through this. So a is 2x minus 5y minus z equals -8. And then 2 times b, so that would give me a -2x plus 2y times 2 would be 4y plus 3z times 2 would be 6z equals 13 times 2, which is 26. And now I can combine these two by adding. So when I add them, 2x minus 2x is 0. -5y plus 4y is -y. -z plus 6z is 5z. And then finally, -8 plus 26 is 18. So in both cases, I wanted to eliminate the same variable. So I took two different sets of equations. In the first one, I combined the second and third equations and eliminated x. In the second one, I combined the first and second equations and eliminated x again. I want to make sure I eliminate x in both cases so that when I have a system of equations, we're dealing with the same variables here. So now I have two variable equations, okay? And we want to go ahead and solve these two variable equations. So this is a new system. I'll go ahead and switch colors. So this basically what we did is we took this system with three variables and now created a system with two variables. So 5y plus 2z equals 18, and negative y plus 5z equals 18. Okay, so now I'm going to do the elimination method again. You could do substitution in this case if you wanted to, but I'm just going to go ahead and eliminate. What I'm going to do is multiply the second equation by 5. So first equation is 5y plus 2z equal to 18. I'm multiplying by 5 here because now you can see the y's have opposite coefficients. So negative 5y plus 25z plus 90. I can combine these two equations. So 2z plus 25z is 27z. Sorry, the 5y's cancel out. 5y minus 5y is 0. And then 18 plus 90 is 108. Now, to get rid of the 27 in front of the z, I can divide both sides by 27. So 108 divided by 27, if you put that into your calculator, is 4. So we took the three linear system down into two variable, two linear system, and then we solved that using elimination for z. Now, I need to go ahead and substitute back in to get the other variables. So I'm going to take 4 and put it back into this equation. So what that gives me now is negative y plus 5 times 4 equals 18. 5 times 4 is 20. So basically I'm going to subtract, well, I'll go ahead and simplify. Negative y plus 20 equals 18. Subtract 20 from both sides. So negative y equals negative 2. And then I have to get rid of that negative. So divide by a negative 1, y equals positive 2. So now I have an answer for y. Once I find the answer for z, I can substitute it back in and figure out what y is. Now I can substitute both of these back into any of the equations up above that we started with to figure out what x is. So I'm going to use equation c here. So x plus 3 times y, which is 2, minus z, which is 4, equals 5. X plus 3 times 2 is 6, minus 4 would be, so x plus 2 equals 5. Subtract 2, so x equals 3. And there we have the answers to each of our variables. X is 3, y is 2, and z is 4. So if we put this together in a ordered triple, 3, 2, 4 would be that answer as a triple. So again, the method here is to combine two of the three equations that they give you originally to eliminate a variable. And we did that with B and C. Then combine two other equations to get rid of the same variable. So we got rid of x in B and C, so we took A and B and got rid of x. Now we can take those two equations and create a system of two variables that we know how to solve using either using either elimination or substitution. Okay. Now you could combine this in a different way. So maybe you did B and C, you added B and C together. But instead of combining A and B for the second one, you could have taken A minus 2 times C. That would give you a slightly different expression, but your answer still would have come out the same. So even if you view the original system of equations a little bit differently and go through different methods to eliminate variables, as long as you're working through the same process, we should all get the same answers. Now, if you feel confident and you're ready to try to solve one on your own, let's go ahead and you can go ahead and pause the video and take a look at C. C is going to have a little bit of a wrinkle, a little bit of a difference here. So um, we'll go ahead and we'll solve it straight through together here. Again, I have three equations. I'll letter them just to avoid confusion. A, B, C. So the goal here is to use or to combine two equations to eliminate a variable. Now in the previous two problems, we eliminated x. But if I take a look at this picture, these equations here, I might notice that the y's could be easy to eliminate because they already have opposite coefficients. So I'm going to go ahead and just take equation B and C and add them together. So this would be 3x minus 2y plus 4z equal to 2. And then 4x plus 2y minus 6z equal to negative 7. So if I add them together, 3x plus 4x is 7x. 2y minus 2y is 0. 4z minus 6z is negative 2z. And 2 minus 7 is negative 5. So far so good. I got rid of the y's. Now I need to use two different equations to get rid of the y's there as well, because now I've got variables x and z, so I want my new equation that I'm going to create to also have variables x and z. So different ways you could go about doing this. What I may notice is that a and b, their y's have opposite signs, but the coefficient is a different number. So let me double a, let's take 2a and then add b to that. So if I take 2a, that would now be 2x times 2, which is 4x, y times 2, which is 2y, negative 3z times 2, which is negative 6z, and negative 3 times 2, which is negative 6. So I doubled a when I wrote it. Now I'm going to just take b and write it down, 3x minus 2y plus 4z equals 2. And I'm going to add these two equations together. So 7x minus 2z equals negative 4. So far so good. Now we have an equation with two variables and another equation with the same two variables. So we want to combine these in a new system. So my new system is 7x minus 2z equal to negative 5, and 7x minus 2z equal to negative 4. Now, if you recognize that there's already an issue with this, that's okay, but from an algebraic standpoint, let's go ahead and let's say I want to eliminate a variable. So I notice that, okay, maybe my x's have the same number, but they have different coefficients. So I'm going to multiply the bottom one by negative 1 to eliminate. So 7x minus 2z equals negative 5. I didn't change the top one, but I'm multiplying the bottom by negative 1. And now I'm going to combine these. So 7x minus 7x, that cancels. Negative 2z, should be a z here, sorry. Negative 2z plus 2z, that subtracts to give you 0. So I have a 0 over here equals negative 1. And so this is an issue because 0 does not equal negative 1. So when we go through the process, we actually went through this process correctly. When we go through this process, we come out with a statement that is false. It's not good. This is a false statement. 0 does not equal negative 1. This tells us nothing about the variables, but what we know here is that there's actually not going to be a solution. So if you go through the correct patterns, the correct steps, and you eliminate the variables and you work down through systems of equations and you get a false statement, then what we know is that this is going to have no solution. Remember back to the last target, we called this an inconsistent systems of equations. So when we graph those, what we showed with inconsistent systems of equations is that with two lines, they are parallel. They have the same slopes but different y-intercepts. For three variables, the planes, actually what we're creating are planes, and the planes would be parallel in this case, and so there'd be no intersection of the planes, and so this would have no solution. So it's okay to come up with dependent answers. That's what we had in A and B, where there was just one solution. So this point right here, or that ordered triple right there, this ordered triple right there, that establishes a plane. And that was giving us the one sole solution. But now the solution doesn't exist. There's not a sole solution. So this is what we would call inconsistent. Let's take a look at D. D has something similar of nature. So if I take a look at D, it's already written in the right order. Notice that there's no Z here for the bottom equation. So what I would want to do here then probably is take the first two equations. So let's go ahead and letter them. Let's make this A, B, C as my equations. I would want to eliminate the Z for the first two equations because Z is already eliminated there. So I've got a two variable equation here. I want to combine A and B to make them two variables. This works out nicely because in between A and B, Z already has opposite coefficients. So 3x minus 2y plus z equals -1 is A's equation, and then we're just going to add B's equation. 2x plus y minus z equals 5. So as I add these two equations, I come up with 5x minus y. The z's would subtract to 0 equals 4. So now I get a new system. In this new system, I'm going to use c right here because that already has just an x and a y variable. So 10x minus 2y equals 8. And then I'm going to use this equation that we just came up with that only has two variables. So 5x minus y equals 4. Here's my new system. Now I'm going to go ahead and eliminate again to get rid of another variable. So what we may notice is that, let's just take a look at the x's. 5 and 10 are not equal, so I'm going to double 5, and I'm actually going to multiply it by a -2 to make sure the signs are opposite. So let's leave the first equation as 10x minus 2y equals 8. Take the second equation times -2. That gives us -10x plus 2y equals -8. And you may notice something here. As I add these two equations, 10x minus 10x is 0. -2y plus 2y is 0. So 0 equals 8 minus 8, which is 0. 8 minus 8, or sorry, 0 equals 0. This is true. So in the last one we came out, when we solved, we came out with two numbers, but it wasn't equal. It was an untrue, a false statement. In this one we come up with two numbers that are equal. This is a true statement. And so this tells us that the solution is going to be all real numbers. Now, there is some stipulations to what these all real numbers are. It's not just any number for x goes with any number for y goes with any number for z. Same as in the last section. There's some stipulations and some requirements behind what numbers go together, but all real numbers will end up being solutions. We're not going to find those stipulations. That's for a class further down the road. What we do want to recognize is that, okay, if we get a solution, or we go through the solving process and we get two equations that are equal, but it tells us nothing about the variables, then this is going to be a dependent system, which technically is all real solutions. And so this is the solving pattern, the solving method that we are going to use for systems of linear equations in three variables. Elimination is the only option that's going to work. Now, what we did here, let me jump back a couple slides. Let's take a look at problem B. Once we got to this new system, so we eliminated with B and C, we eliminated with A and B, and we created a new system. Once you get to this new system, you can solve this two variable equation using substitution. So if you like substitution, you can use substitution, but you have to start with using elimination. There's no other way that we're going to be able to do it in this class. Okay, so elimination is going to be the method to go initially, and then we can solve our doubles, or our system of equation with two variables once we get there any way that we want. This brings us to the applications. So we have two application problems, and then we are finished. For my school level guys, we're going to go through these applications, but they're not going to be part of your quiz just yet. We're going to have some more time to practice, assuming we get around to a test at some point in time, depending on what happens with how we're out of school right now, eventually applications will show up on your test. For honors guys on the online assessment, the quiz over this topic, you will have applications. So we need to make sure that we get these, we understand these as soon as possible. So the big thing with the application problems is creating the system of equations. So for this section, it's all three variables. It's all three linear systems. Eventually, we're going to have to determine how many variables there are and how many equations are in our system. But for right now, three variables, three equations. So in problem number 3, it says a small business borrowed $225,000 from 3 different lenders to expand their product line. The interest rates were 5%, 6%, and 7%. Find the amount borrowed. Here's another typo, which will be fixed in your notes by the time you get it. Find the amount borrowed at each rate. The annual interest came to $13,000, and twice as much was borrowed at the 5% rate than was borrowed at the 7% rate. So the first thing that I want to do here is probably identify what my variables are. So in this case, if we read through this problem, there's 3 different lenders and there's 3 different rates that we're borrowing money for. And so if we're trying to figure out how much is borrowed at each rate, but we don't know how much is borrowed at each rate, that's our 3 different variables. So x, let's let x be the money that's borrowed at 5%. So I'm just going to abbreviate here, dollars at 5%. Let's let y be the dollars at 6%. And let's let z be the dollars at 7%. So it gives us 3 different rates. Now, we need 3, if we're going to have 3 variables, we need 3 equations. So what we know is that they borrowed $225,000. It's one of the first things that we know. Now, we don't know how much was borrowed at the individual rates, but we know whatever was borrowed, the total is $225,000. So what we can do there is write one equation. X plus y plus z is $225,000. Now, we're not going to worry about what x, y, and z are just yet, but that's a first equation. The second equation here, jump down to this part. The annual interest is $13,000. So remember, to find interest, we need to take the rate times the amount was borrowed. We're not trying to find the total value of the account again like we did a couple targets ago. We're just finding the interest. So the amount that was borrowed, x was borrowed at 5%. Remember, if we take x and we put it to or percent and we put it to a decimal, you have to move that decimal place over two positions. So 0.05 is 5% times x would give us the interest. So if it was $100 that we borrowed at 5%, the interest would be $5. So then we'd also have plus 0.06, because 6% was borrowed for y, and then plus 0.07 z, because 7% was borrowed, or z was borrowed for 7%. Now what we know is this total has to come to $13,000. So I'm going to leave the dollar symbol off now, but we'll come back to putting in those units later. So here's our second equation. Then our third equation comes from this part. Twice as much was borrowed at 5% than what was borrowed at 7%. So 5% is x. X, that amount, is twice as much as 7%. So x has to be 2 times z. So in order to be able to get twice as much, we have to double whatever was borrowed at 7%. And going back to our little key over here, z was borrowed at 7%. So x is double z. Now, this gives us 2 equations. One of the difficult things here in this equation is, A, they're not written in the same format. We need to move this around to make it look like those. But also, B, we have decimals. So what I'm going to do is I'm just going to multiply this second equation by 100 as I rewrite all these equations. So the first equation is x plus y plus z equals $225,000. The second equation, again, had 0.05x, 0.06y, 0.07z. You can work with those. If you're okay with decimals, or if you would like to put them as fractions and you're okay with fractions, you can definitely work with those. What I'm going to do instead is I'm going to multiply by 100 to get rid of those decimals. So just to show you here, if I take 0.05 times 100, that would give me 5. And so I'd end up getting 5x plus 6y plus 7z. Now 13,000 times 100, you could do this in the calculator if you needed to, is 1,300,000. Now again, I did not change the equation. I just multiplied by everything by 10 to get rid of the decimals. Finally, the last equation, we do have to reorder this one because z is on the other side of the equation. So what we want to do here is subtract z. And so technically this would be x minus 2z equals 0. So subtracting 2z from both sides. So this is our system of equations right here. This is what we are going to work with. So what we need to do here is, hold on just a second. What we need to do here is we need to, again, eliminate some of the variables to get to a two-variable equation here. So we have our three equations here. Two of them have three variables. One of them has two variables. So what we see here is we have an x and a z in this third equation. So I'm going to go ahead and I'm going to number these again, or letter these, sorry, letters. It's probably a little less confusing. A, B, C. The third equation, C, only has variables x and z. So what would be nice is if we could get another equation with only variables x and z. So if I take a look at A and I take a look at B, I can eliminate the y's, or I need to eliminate the y's. So what we may notice is that one of the y's has a coefficient of 6, the other has a coefficient of positive 1. So what I need to do here is I need to take A and multiply it by negative 6, and then add that to B. So that will get the y values to eliminate, which will get us a two-variable equation that we can create a new system from. So negative 6a plus b. So negative 6 times x would be negative 6x. Negative 6 times y would be negative 6y. Negative 6 times z would be negative 6z. Let's go ahead and type this one into the calculator because this is a rather large number. So 225,000 times negative 6 would give us negative 1,350,000. So now I want to take to that and I want to add b, which is 5x plus 6y plus 7z equals 1,300,000. So when I add these two equations together, negative 6x plus 5x is negative x. The 6y's will cancel out and become 0. And then negative 6z plus 7z, just be plus z. And that would equal a negative 50,000. So we can simplify this expression to give us just two variables. Now, what we can do here is we can work on eliminating, or sorry, we can go ahead and we can rewrite and to give us a second system. So I've got x and z that are variables here. So negative x plus z, the equation that we just wrote, equals negative 50,000. And I have part C right here from our original system that only has two variables. X minus 2z equals 0. So it gave us a new system. Now there's a number of different ways that you can solve this. You can solve this graphically if you wanted to, because it doesn't tell us how we have to solve here. It doesn't tell us we have to solve algebraically. So if I wanted to create a graph with these two, I could. But this is actually a quick elimination. If I want to go ahead and add the two equations together, negative x plus x gives me 0. Z minus 2z gives me negative z. And negative 50,000 plus 0 gives me negative 50,000. So this gives me a solution for z if I divide by negative 1. Z is 50,000. Now that gives me one solution. We need to figure out x, y, and z. So now I can go back and I can substitute in any of these equations, or sorry, any of these two equations to figure out what x is. So let me choose the second equation. So x minus 2 times 50,000 is 0. So I'm taking z here and substituting into that equation there from our system. So x minus 100,000 is 0. So x equals 100,000. Now I also need to solve for y, so I can choose any of my systems that have a y in it, any of my equations that have a y in it, and substitute in my z value and my x value to solve for y. So I'm going to go back to this first equation, and let's take the 100,000, put it in for x. So 100,000 plus y, we don't know y yet, plus 50,000 equals 225,000. So y, if I simplify, y plus 150,000 equals 225,000. And then I can subtract both sides by 150,000. You can do that in your calculator if you need to. And you get y equals 75,000. So we could check, these are some pretty big numbers. We could check to see if this is correct by substituting x, y, and z into any of these three equations, or all three of these equations, and we find out that all three of these equations would be equal if we substitute in x, y, and z. So this is our answer. We do need to put our answer back into the context. So the question asked, find the amount borrowed at each rate. So at 5%, $100,000 was borrowed. So 5% was our x value, again, going back to our key. 5% was our x value, and x was 100,000. We do need to make sure we put the units back in there, which is dollars. Excuse me. At 6%, this was our y value here. At 6%, $75,000 was borrowed. And finally, at 7%, which is my z value, $50,000 was borrowed. So the total, $225,000 was borrowed at this breakdown. 100,000 at 5%, 75,000 at 6%, and 50,000 at 7%. So again, the process here is to read through the problem, pick out our three variables, start by assigning the three variables, and then create a system of equations based on that. Then we can solve that linear system with three variables using the algebraic method of elimination. At the very end, we want to make sure we put those answers back into context. Let's go ahead and let's do the final problem, problem number 4. It says at a local fair, a bank invites attendees to guess the amount of $5, $10, and $20 gold pieces in a sack. Participants are told that there are exactly 250 coins with a total value of $1,875. If there are also 7 times as many $5 pieces as $20 pieces, how many of each gold piece are there? So go ahead and see if you can identify, pause the video and see if you can write out what the three variables would be. If you said the three variables would be the $5 piece, the $10 piece, and the $20 piece, then you would be correct. So let's let X be the number of $5 pieces. Let's let Y be the number of $10 pieces. And let's let Z be the number of $20 pieces. So those are the three variables that we're looking for. The number of each of the three gold pieces. Now, see if you can write three equations, or how many of the three equations you can write. So again, you should be writing three equations for this system with these three variables. So pause the video and see if you can figure out how many of the equations, or see if you can figure out at least one, if not all three of the equations. Okay, so the first thing that we know is there are exactly 250 coins. So our three variables, we don't know how many of each of the coins there are, but we do know that the first coins, or the $5 pieces plus the $10 pieces plus the $20 pieces, has to be a total of 250. So we don't know how many of each coins there are, but we do know all together they have to add up to 250. The second thing that they tell us is the total value is $1,000, $1,875. So if we have X pieces, or X number of $5 pieces, let's say we have 10 $5 pieces, you'd say the value of that is $50, because you would take the $5 times 10. So 5 times X plus 5 times Y plus, or, sorry, not 5 times Y, but 10 times Y, because that's a $10 piece, plus 20 times Z, because that's a $20 piece, has to equal 1,875. Then finally, the last thing is that there are 7 times as many $5 pieces as $20 pieces. So our $5 pieces, X, would be equal to 7 times Z, 7 times the number of $20 pieces. So now if I wanted to rewrite that, if I need to put X equals 7Z into the same style or the same format of equation, I need Z on the other side, so I would subtract the 7Z. So I'm just going to go ahead and write this down as X minus 7Z equal to 0. So here is our system of equations. And again, I'm going to letter these as A, B, and C. At this point, now that you have the system of equations, x plus y plus z equals 250, 5x plus 10y plus 20z equals 1875, and x minus 7z equals 0, see if you can pause the video and solve to find out the solutions for x, y, and z. Hopefully you had a chance to solve. Let's go through. So the first thing that we may notice here is that C has two variables, just an X and a Z. That's good. There's no Y here, so we want to use C in a new system. We want to combine C with something else. And so we need to create another equation where essentially we eliminate the Y value. So what I'm going to do is it's going to take a look at A and B and eliminate the Y value. So B has a positive 10Y. A has a positive Y. So what I need to do is I need to take negative 10A plus B. Now you could also take positive 10A and subtract B. If you did that, that's definitely okay. So negative 10 times X would be negative 10X. Negative 10 times Y would be negative 10Y. Negative 10 times Z would be negative 10Z. And negative 10 times 250 would be negative 2,500. Now, this isn't the only way to do the elimination. So if you did something different, go ahead and see what's done here and see if you have the same answer when we get to the end. So I'm going to add these two equations together. So that gives me a negative 5x. Negative 10y plus 10y is 0, so I don't have to worry about y's. And then that gives me a, sorry, let me make sure this looks like a negative out in front of the 5x. There we go, negative 5x. And then negative 10z plus 20z would be positive 10z. Now I do want to combine the 2500 and the 1875, which that's maybe a little difficult number. Make sure we get it right. It is equal to negative 625. So now what I can do is I can create a new system of equations. And this system of equations is going to have x minus 7z equal to 0 and negative 5x plus 10z equal to negative 625. Now, a variety of ways that you can solve this. I'm going to do it algebraically, but then I'm also going to come back to this and show you how we could do this graphically. So let's say I have this new system of equation algebraically. I'm going to go ahead and eliminate the x values because this has their opposites. One's a positive, one's a negative. This x has a 5 in front, this has a 1, so I'm going to multiply this top equation by 5. Again, not the only way you can do things, but just how I'm going to work through it here. So 5x minus 35z equals 0, multiplying everything by 5. And then the bottom equation would be negative 5x plus 10z equal to negative 625. Now I can add together these expressions. So the negative 5x and the positive 5x cancel out. That would give me negative 25z equals negative 625. And now I can divide to figure out the value for z. So negative 625 divided by 25, sorry, negative 625 divided by negative 25 would be positive. So z is 25. So there I have one of my solutions. Now I want to figure out my other solutions. So I'm going to go ahead and go back into that first equation and substitute. So x minus 7 times 25 equals 0. So substituting into this expression here, ignoring the multiplying by 5. You could do the multiplying by 5. You could use this equation, but it's a little faster if you don't. So negative 7 times 5. So x would be minus 175. So x equals 175 if we add 175 to both sides. Finally, I want to figure out what y is. So I'm going to take, maybe I'm going to go back to the very beginning and take equation A and use equation A to solve for y. So x is now, so I'm taking this x, putting it in there. I'm taking this z, putting it in there. So x is now 175 plus y plus z is 25 equal to 250. So y plus 200 equals 250. If I simplify, subtract 200, and y equals 50. So here we have the answers to our system, and we want to put this into context. So what was x? X was the number of $5 pieces. So we want to figure out how many of each gold piece are there. So x is the number of $5 pieces. There's 175. So 175 $5 pieces. Y is the number of $10 pieces. So there is 50 $10 pieces. And Z is the number of $20 pieces. So there's 25 $20 pieces. And so here we have the answer for the number of pieces for each set of gold based on the information they give us. So again, the first thing we did was we identified the three variables. Then we used the information to write three different equations, which we could then use the elimination method to get down to a system of two equations with two variables and solve from there. Now let me go back to the system of two equations with two variables. We can solve this system graphically if you want to. So if the elimination method was pretty quick there, but if you like graphically, you can definitely solve this graphically. Now, what I would do if I wanted to solve this graphically is I would get one of the variables by itself. Let's say maybe get x by itself, and this is where we have to be a little bit careful. So if I were to rewrite the equation, I'm not going to show you the steps, but if I were to rewrite the equations, I would get x equals 7z, and I would get x equals, let me make sure I get it correct, x equals negative 2z minus 625. Sorry, not 625, minus 125, plus 125. Could both be positive. There you go, 2z, yeah, 2z plus 125. So if you wrote both these equations for x, you could graph them. Now remember, in your graphing calculator, it only gives you a y value. So I could graph this as x equals 2z, but instead in my calculator, I'm writing this as z or 7x instead of 7z. And then I'd write this as 2x plus 125 because that's the only way that your calculator is able to do things. I'm going to take the x minimum and go from, let's say, 0 to 200, and then graph it. That's not how I wanted to graph it. Here we go. And graph it. So now the thing to remember here is that the x-axis is actually my z variable, and the y-axis is actually my x variable for our problem. So when I find the second trace intersect here, I find the point where they intersect, I do have to remember that, okay, I typed in x where I had a z, and this x was actually where the y was on the calculator. So x is 175 and z is 25. Okay, so it's definitely okay to do this graphing. You could have rewrote these equations and graphed them like that to find the intersection on your graphing calculator. That's definitely all right, but you just have to remember where your variables are in terms of the solutions that the equation gives you. Okay, so this is the completion of target SE2. Target of SE2 again is a extension of SE1. It's systems of equations, but now we're coming into three equations with three variables. And we are going to solve these primarily through the method of elimination, and then using substitution to come up with the other variables that remain. At this point, this is the conclusion that SE2 notes. Remember, there is an upcoming online assessment for SE2. That will be open notes. So hopefully you have taken good notes through this video. If you have not, make sure you go back and get down examples and things that will help you. If you have questions, write those questions down and have those prepared for our upcoming Zoom session. Both the honors and the school level, guys, both of you guys should be working on your homework. So for school level, it's going to be IXL that's posted after you finish these notes. For honors, it's going to be that worksheet that's finished after you, or posted after you finish these notes. Make sure that when you are working through those homework problems, if you're getting stuck on things, jot those questions down so that when we get together again on the Zoom session, you have the opportunity to ask those questions and have those questions answered before we have the assessment. If you need any immediate questions concerned or answered, make sure you shoot me an email. That is all that we have for today. So thank you for tuning in and have a good day.